and thank Emmanuel and Seneras for organizing this, and I leave you the floor to Emmanuel.
Thank you very much, Roch. So I will say a few words to introduce Professor Park. It's a great pleasure and a great honor to welcome today Professor Nam-Gyu Park, who is a distinguished professor at Sungkyunkwan University, SKKU, in South Korea. Professor Park knows very well France, in fact, because he made a postdoc in Bordeaux from 1996 to 1997. Yeah. Then he worked at National Renewable Energy Laboratory in USA. And from 2005 to 2009, he was director of Solar Cell Research Center at Korean Institute of Science and Technology, KAIST, famous. He is full professor at SKKU since 2009 and a fellow of Korean Academy of Science and Technology since 2017. He has been working on high-efficiency mesoscopic nanostructured solar cells since 1997. And all of you know his works, of course, because he is pioneer of solid-state perovskite solar cells, which were first developed in 2012. Professor Park is then at the origin of perovskite breakthrough and spectacular emergence of this material. He is a highly cited researcher in the top 1% of world scientists, and he received a lot of awards for his pioneer works. Today, he will shed light on the beginnings of the fabulous history of the hybrid perovskites and will present the latest advances that have recently enabled to exceed 25% yield. This event is a joint event between the French think tank HPERO Allied Perovskites, with 40 laboratories in France, all around France, supported by CNRS, Centre National de la Recherche Scientifique, and a joint event also with IPVF, Institut Photovoltaics d'Île-de-France. I thank particularly IPVF for the welcome in the Edmond Becquerel room and for the organization of this live streaming. So now, if all is okay, okay, I can say now that Professor Park, floor is yours.
Thank you very much for kind introduction, Professor Emmanuel Delaporte. And then I'm very happy to be here again to give a talk about the perovskite solar cell in front of very esteemed researchers in terms of the photovoltaic expert. Well, so I'm Nam-Gyu Park again, and from the Sungkyunkwan University. Sungkyunkwan University is the oldest university in Korea. So the history is more than 600 years ago. So this is the first even in the world, not in Korea. And I'm working at the School of Chemical Engineering of the Sungkyunkwan University since 2009. So today I like to give a brief introduction of how to discover the solid-state perovskite solar cell, and then recent progress and what we have to do in the future, next 10 years. So first of all, I like to before getting started, the importance of solar energy resources. The solar energy is a tremendous the amount as compared to the non-renewable energy. So the non-renewable energy actually give a serious problem because of the carbon dioxide emission. Therefore, we have serious problem in climate change because of the global warming. And also this fossil fuel is actually must end. But renewable energy is almost never end. And among them, among the renewable energy resources, solar energy resources are pretty much abundant, and then it's almost unlimited. So we have to find out how to utilize efficiently solar energy. The answer is the photovoltaics. So I investigated the activities of the photovoltaic researches since 1991. And then I found that there is a very small increase in the publication. However, there is two here. Since 2010, we have the abrupt increase in publication of the photovoltaics. So the photovoltaic here is the every kinds of the photovoltaic materials, not only perovskite but also some silicon, CIGS, and CDT, and so on. And then the accumulated publications, as you see here, is about 145,000, which is this is almost double the lithium battery area, and also the higher than the fuel cell area. So this year actually we have the very good news about the Nobel Prize in Chemistry, and then the people's won the Nobel Prize because of the significant contribution to the electric energy due to the lithium battery. So photovoltaic, actually, why we have such the huge increase since 2010? Then there is two reasons we can find. First one is the grid parity, meaning that the photovoltaic, the solar, the price of the cost of the solar electricity becomes comparable to, equal to the grid electricity, the cost, and around here. And even in the future, we expect that the cost of solar electricity will be lower than the grid electricity. So usually the grid electricity comes from the fossil fuel, burning the fossil fuels. And therefore, we can see here that the accumulated solar panels increased abruptly since 2010. So this actually industrial the activity push the research activities. So we can see a lot of the photovoltaic research publications. And second one is this is my private opinion, but you see here the perovskite solar cell since 2009, but after 2012, because of the stable solid state perovskite solar cell discovery, then we can see the exponential increase in the publications. So which contributed to the abrupt increase in the publications in the photovoltaics. I'd like to briefly introduce the how we discovered the solid state perovskite solar cells. And the solar cell actually is composed of the P-type and N-type semiconductors, so P-N junction structure. In that case, the three parameters are important for developing a solar cell: the power conversion efficiency and cost and stability. So first, when you want to make the highly efficient and low cost a stable solar cell, then you first select a very effective light absorb. And then when you select light absorb, three important parameters you have to consider: band gap energy to utilize the panchromatic light absorption, and then absorption coefficient, and then the transition type, dielectric or indielectric. Mostly dielectric transition is better than the indirect transition. So among them, the absorption coefficient is most important, because if you have the high absorption coefficient, then you can decrease the penetration depths. And then actually I was working on the solar cell since 1997 at National Renewable Energy Lab. Dr. Arthur Franco was my the supervisor. At that time, I worked on the dye-sensitized solar cell, which is liquid junction type, very specific solar cell structure that was developed by Professor Michael Rachel at EPFL. And then at that time, I got 9.2% efficiency, which was second world best because the 10% was the world best efficiency at that time. And then, as I mentioned, that why the publication of the photovoltaics is not that much is enough or the many. That is because silicon solar cell, the price is very high. So the issue in the photovoltaics is how to reduce the cost. So he actually, Michael Grachel published the low cost, the dye-sensitized solar cell. However, the efficiency was a little bit lower than the silicon type or the conventional the solar cell structure. It's about 7 to 8%. Then the efficiency is slightly increased to 10 to 11% in the 1997. After that, the efficiency is almost is constant. So the efficiency limitation of the efficiency of the dye-sensitized solar cell is due to the low absorption coefficient of the organic sensitizer. This is actually the not organic. This is a lutein complex. So this is inorganic sensitizer, but the molecular structure. Because the low absorption coefficient usually 1 order of magnitude lower than the conventional semiconductor light absorber. So people would like to find out some the better the sensitizer to replace the organic sensitizer. So one example, very good candidate is the quantum dot inorganic quantum dot material. Actually, so actually we also studied quantum dot inorganic quantum dot materials. For instance, lead sulfide. Lead sulfide is the bulk lead sulfide is not good for the photovoltaic material because band gap energy is about 0.5 eV, which is not good for the photovoltaic materials. But if you decrease the size, then you can see the quantum size effect. Then, for instance, lead sulfide, if you decrease the size, the less than 3 or 2 nanometer, then the band gap increases to 1.1 eV. We found that the photocurrent density is pretty much good. It's approaching theoretical value. However, the open circuit voltage is 0.4 volt, which is 0.7 volt is lower than the band gap energy. That means 0.7 volt is voltage loss of the 0.7 volt. So this material actually cannot overcome, cannot overcome the existing the organic sensitizer such as the N719. While searching the better candidates to replace anyway the N719 sensitized. Excuse me. I was invited to. This is not the common the conference. This is special conference that is called the Nano-Euro 2007, which was held in St. Switzerland. This very beautiful historical place. And I was invited by the Professor Michael Grachel to give some research activities of dye-sensitized solar cell in Korea. And I found that one of the talks was given by the Professor Tam Miyashaka from the Toin University, Yokohama in Japan. And he gave a talk about the perovskite sensitized solar cell. And then he announced that this perovskite sensitized solar cell produced about 2 to 3% efficiency. So this is far below than even the N719 dye based the solar cell. That is around 11% efficiency. So actually, people did not pay any attention to. So no one asked the question about this the material. But I was very interested because my background in MS and the PhD course was the oxide perovskite. So I was familiar with the perovskite, the terminology. And then the perovskite is, as you know, this is a chemical formula is AVX3. Usually, if you use the the oxygen in anion, then you have the 2 plus, 4 plus, or the 1 plus, 5 plus, the cations. This is actually the A site cation has the cubo-octahedral geometry, and B the cation has the octahedral geometry, and which has the corner sharing. So this specific structure is called the perovskite. So perovskite is the structural name. And then he actually used the sensitize of this material, the sitting on the titanium oxide, and then he showed us the IPC spectrum, external quantum efficiency, as function of wavelengths here. And then the methyl ammonium lead iodide, we have the organic cation, especially here in this specific the perovskite material. As you can see here, the absolute the IPC is even lower than 50%. This is not good for the conversion efficiency, but the feature, the shape of this IP spectrum is pretty much ideal case because at the low wavelengths to the high wavelengths almost constant value. This is good news. So when I take a look at this IP spectrum, this material will be very good material if we increase further the absolute value of the IP spectrum. So after coming back from the Sengalen Nano Euro 2007 conference, I started work on the perovskite, the solar cell, and I asked my the postdoc to prepare the perovskite and then test this material in dye-sensitized solar cell. And she actually prepared, I'm sorry, this is Korean version. She prepared the methyl ammonium lead bromide and methyl ammonium lead iodide. So this is not so important, so the result is important. And then because she was expertise in a dye-sensitized solar cell, especially liquid type dye-sensitized solar cell. So actually she would like to see what's going on about in terms of stability of this material, because this material is ionic crystal, so maybe it's not stable in the polar liquid electrolyte. So she prepared some thin film on plain glass and then dropped the electrolyte, and then immediately the perovskite disappeared because of quickly dissolution in the presence of polar liquid electrolyte. So we stopped for the time being at that time, and then I joined Sungkyunkwan University in 2009, and then 2009 actually the Tom Miyashaka published for first time the perovskite sensitized the solar cell in JAX communication with efficiency still the 3 to 4%. And then I also resumed the perovskite solar cell here. And then we prepared some differently from the recipe provided by Professor Tom Miyashaka. That is about 8% to 8%. So we changed the concentration of this precursor solution, and then we found that 48%, this is almost the supersaturation concentration in the polar protic solvent here. And then the 48% produced reproducibly the perovskite film. And the first version of this perovskite solar cell is based on the quantum dot morphology of perovskite sitting on the titanium oxide surface. And then we actually reported the double the efficiency, 6.5%. But this is still in dye-sensitized solar cell structure, meaning that we still have the liquid electrolyte. That means the stability, we cannot guarantee the stability in the presence of a polar liquid electrolyte. So as you see here, this is typical dye-sensitized solar cell structure, sandwiched between the two FTO conducting glass. And then the black color comes from the methyl ammonium lead iodide. If you inject the electrolyte, and then in few minutes, some perovskite is dissolved quickly. So it is not a useful material for in terms of liquid electrolyte-based solar cell. So we would like to change the liquid electrolyte with a solid hole conducting material So first we tried the P3HD, which is well known for the organic the photovoltaics. And then first we did not actually get the high efficiency because we prepare the mesoporous titanium oxide, and on the surface of mesoporous titanium oxide we adsorb the dot morphology of the perovskite, and then which is fully wrapped with solid hole conducting material. So in that case, the polymer should be infiltrated into the mesopores of titanium oxide. Mesopore of titanium oxide. So polymer is very difficult, hard to be infiltrated completely in the mesopore of the titanium oxide. So we cannot, at that time, we cannot obtain the high efficiency. So we switch it from polymer to the molecular structure hole conducting materials here. And then the efficiency here is the, so we have to block the sunlight. Even we are talking about utilizing sunlight, so this is not good way. Anyway, from the around 6% efficiency, but we changed some pore structure and also some the titanium oxide film thickness, something like that. But we could not increase the efficiency. So we are at that time we are suffering from the improvement of the efficiency using the solid hole conducting materials. But because we know the perovskite materials has the 1 order of magnitude higher absorption coefficient than the conventional N719 dye. So that means if you increase the absorption coefficient, then you don't have to increase the titanium oxide film thickness, because penetration depth is inversely proportional to absorption coefficient. So thinner film will be okay, it's better. For instance, gallium arsenide is a thin film type. Why we need a thin film using the gallium arsenide? Because of the very high absorption coefficient. So thin film is enough. So we do not increase the film thickness like the silicon solar cell. So we decreased the film thickness from 2 micrometer to 1 micrometer, and then we observed the gradual increase in power conversion efficiency, which is due to the increase in open circuit voltage and fill factor you see here, without sacrificing the short circuit photocurrent density. So this relationship is actually proved. And then we further decrease the efficiency up to 0.6 micrometer, and then gradual increase up to the 10% efficiency, and then which is due to the increased open circuit voltage and increased fill factor without the change in short circuit photocurrent density. So we actually published, we got the 9.7% efficiency from this 0.6 micrometer titanium oxide film, and then this is first version. At that time we attached the dot morphology, the perovskite that is sitting on the titanium oxide surface, and then the perovskite, the sensitized titanium oxide, is fully wrapped by the hole conducting material. And then the hole conducting material's pyro compound is a little bit the hydrophobic nature, so we can guarantee some long-term stability even without encapsulation from this specific structure. So we published the 500-hour stability and 9.7% efficiency, and then we actually published this work, scientific report published by Nature, Springer Nature now. And then now this work is cited 5,000 times actually. So this work actually first submitted to Nature because we actually asked Professor Michael Gratzel to collaborate to measure some fundamental study, for instance, charge separation, or see what's going on about the impedance inside the solar cell, perovskite solar cell. So and then we closely contact Professor Michael Grazer's lab by sending my student Hee-Sun Kim. Now she is a professor in Inha University in Korea, and she bring the 100 the cells without encapsulation, and then went to the Switzerland to measure something the charge separation using the femtosecond laser dynamics. And then while we are the measuring or studying, collaborating this solid state perovskite solar cell, Michael actually told me that we have to hurry up submit our work, and then yes, so submit to Nature Science. No, you don't have to submit Nature Science. It takes a long time. So the fast track is better. So he recommended me to submit Nature Communication, and then we submitted Nature Communication first, and then we asked the editor that this work is very important. So please, make the very fast process to publish this work. And then the Nature Communication editor told me that we cannot proceed faster. So please go to the scientific report. So we actually the transfer the scientific report. Anyway, now this work cited over 5,000 times. And first work actually the Tom Miyasaka's works now is more than 7,000 times. And then history is here. In terms of publication, 2009, the Tom Miyashaka published the first paper, and only one paper came out. And next year we don't have any the publications. And 2011 we published the second paper, still the liquid type, the perovskite sensitized solar cell. And then only one paper came out. So that means there were no follows because the instability of this liquid type perovskite solar cell. So, but thanks to this instability, we forced to develop actually the solid state perovskite solar cell. So the 2012 is very the breakthrough year, and after publication of the solid state perovskite solar cell, the publication increases exponentially. And last year we have the over 3,700 the publications. So since 2012 we have almost 14,000 publications, and then also this year approaching almost over 3,200. This is as of October. So then, because I'm curious about our work, the contribution of our work, solid state, the perovskite solar cell. So in that case, I took the power conversion efficiency as a function of time, and then did some first derivative, because the first derivative you can see the inflection point, which is kind of turning point, and then we found that our work is actually the kind of the make turning point of the perovskite photovoltaic. So that means our work contributed significantly. Well, now the perovskite, the record efficiency was 25.2%, which was achieved by the Dr. Jang Won-seo from the KLICT in Korea. This is Korean Research Institute of Chemical and Technology. And you see here is very close to even the record efficiency of the silicon. It takes about more than 60 years to get the 26.1%. So less than the 10 years we can get the 25.2%, and which is even higher than the thin film technology such as CIGS or the CDT, even higher than the multicrystalline silicon solar cell. So the perovskite solar cell is pretty much promising the technology, and also so when you make the perovskite solar cell, then it takes very does not need any high energy, and also it's very the faster. Meaning that you can produce very quickly perovskite solar cell as compared to other technology using high energy, and also they take some time to produce the single junction. And in our lab, actually, we focused on the pure MAPBI3. The 25.2% efficiency is based on the mixed cation, mixed anion decomposition. But I was curious about that such a mixed composition may undergo the phase segregation, and also probably it's not suitable for the commercialization because of it's difficult to handle the composition, very minor composition. So we focused on the pure the MAPBI3 or FAPBI3. So starting from the 9.7% using the MAPBI3, now we get the 21.1%, which was certified actually based on the FAPBI3. Previously we used the precursor mixture as usual, but now we are using the perovskite powder, inexpensive perovskite powder, and we can get the high efficiency. So I will talk about this in detail about this powder method. And we have two important the composition. One is the methyl ammonium lead iodide, and second one is the foam ammonium lead iodide. Probably foam ammonium lead iodide is better than the methyl ammonium lead iodide because of the narrow band gap, meaning that you can utilize the long wavelengths of light. However, the methyl ammonium lead iodide is pretty much stable of the perovskite phase, even at the ambient condition, room temperature. However, the foam ammonium lead iodide is not stable at the room temperature. It tends to phase transition from the perovskite alpha phase, this is photovoltaic the material, to the non-perovskite delta phase, which is not the photovoltaic material. So to stabilize the alpha phase of the FAPBI3, people use some kind of the cation, such as cesium cation, the methyl ammonium cation, rubidium cation, etc. Very small amount of cation is included in this FAPBI3 phase. And then we also show that for the first time, if you include the cesium cation, this is 10 more percent with respect to the foam ammonium cation. Then usually the foam ammonium, the lead iodide, stabilized foam alpha phase can be formed at 150 degrees C. Below this temperature is difficult. Usually the delta phase is stabilized, meaning that this non-perovskite yellow phase. But if you include a small amount of cesium, then even at room temperature you can see some the alpha phase FAPBI3. So I can say that this additional cation is kind of the stabilize to stabilize the FAPBI3 alpha phase. So to make the high quality, usually from 9.7% efficiency to the 25.2% efficiency, why we can get such a high efficiency, then actually the approaches contributed to high efficiency. One is how to prepare the high quality film, and then some compositional engineering. So we have two very effective ways to get the high performance perovskite the film. One is the anti-solvent engineering. The second one is the Lewis acid base adduct. So usually when you make the perovskite film, while spinning, you drop some anti-solvent, not dissolving perovskite phase, but some are dissolving some organic solvent. And then the anti-solvent engineering actually was proposed by the Professor Sang Il-seok and also the Professor Yi-Bing Chung. And we actually proposed the Lewis acid-based adductor method. It's similar to the this anti-solvent engineering, but we arbitrarily induce the Lewis acid-based adduct. So if you take a look at this precursor material, the PbI2 is well-known Lewis acid, and then the polar approach solvent DMSO, DMF can be used as a Lewis base. So in inorganic the chemistry, if you react with the Lewis acid and Lewis base, you can have the weak chemical bonding Lewis acid Lewis base adduct the compound intermediate. So we utilize this intermediate to control the crystal growth of perovskite. Otherwise, because this is very fast, the process to make the perovskite film, so you cannot control the perovskite film. So we need anyway the intermediate phase. So if you undergo the intermediate phase, then you can make the high quality perovskite films. So for Lewis base candidate, you can use any kind of this polar approach Lewis base materials. And then I like to so far we achieve the very high efficiency. So during the 10 years, and then the next 10 years, what we have to do is further we can increase the further higher efficiency and also the stability, and then scale up technology and so on. And also I like to mention the material issue for commercialization. For the higher efficiency, actually, so this is the well-known the Shackle-Quist limit based upon the band gap energy. The gallium arsenide is, for instance, if you use the 1.4 eV gallium arsenide, then the almost 30% efficiency can be achieved. This is real data, the observed efficiency, and then in that case, the theoretical efficiency is around 33%. In perovskite case, if you use the 1.6 eV, for instance, MAPBI3, then the efficiency, theoretical efficiency around 30.5% according to Shackle-Quist the efficiency calculation. Around here we have this is a 24% efficiency previous data, and now we have something kind of the 25% here. And if you break down, not PC is actually power conversion efficiency is product of the short circuit current and open circuit voltage and fill factor. And if you plot short circuit current with respect to voltage and fill factor, and with respect to the theoretical value here, the first the gallium arsenide, actually the open circuit voltage and fill factor is very close to the theoretical value. However, there is some more gap between the theoretical efficiency and the short circuit photocurrent density. So research direction in the gallium arsenide, I'm not expertise in gallium arsenide, but they would like to increase the short circuit photocurrent density using the gallium arsenide. For instance, the photon recycling method or something like that. How about the perovskite? Perovskite is actually for the short circuit current is very close to theoretical value. However, there is a large gap between the observed value and the theoretical value in terms of the open circuit voltage and fill factor. So we have to increase the open circuit voltage and fill factor to reach the theoretical efficiency, such as 30% from the single junction using the perovskite material. And then the common issue to increase the open circuit voltage and fill factor is the recombination. So we have to control the recombination. Here is very good the calculation result. And for instance, if you use the only the perovskite itself without any the interfaces, without any electron transport layer, without any the whole transporter layer, then you can get the high open circuit voltage. But once you introduce the ETL or HTL on both, then you can decrease further the open circuit voltage. This is due to the mostly comes from the interfacial recombination. So here is the calculation. If you allow only radiative recombination, meaning that you don't have any defects in the perovskite film, you don't have any interfacial the recombination, then the 30.5% efficiency can be expected because of the open circuit voltage is around the 1.33 volt. Now we have the 1.16 less than 1.2 volt in dual system, and then the fill factor is well, the 0.9. The best fill factor is now 0.85. So therefore, we can get if you work on the reduce the recombination, then we can get this kind of the open circuit voltage and fill factor. And then if you increase some defect inside perovskite material, that is called the SRH recombination. Then you further decrease short circuit photocurrent density, a slightly fill factor, and also a large amount of the loss of the open circuit voltage. So here is about 1.0 is a kind of 1.17 something like that. And if you further induce some interfacial recombination because of the ETL HTL layer, then further they decrease the open circuit voltage without the change in short circuit photocurrent density. If you are working on the perovskite solar cell, you can find out that this kind of the phenomena frequently. This is due to the interfacial engineering. So why some people get the 25% efficiency? Probably they can control the SRH recombination and interfacial recombination very well. So I think because the photovoltaic device, solar cell is the device. So device interface is a device, as mentioned by the Professor Kramer, as Nobel laureate in physics. So the interface is very important in device structure. So we have the two simple structure for making the perovskite. Solar cell normal structure and inverted structure. Either case, you can make the planar structure or the mesopore structure. And then the normal structure, we have the four types of interfaces, and also there is some interfaces comes from the grain boundary. So we have to control these interfaces well. So I like to give some example to show the effect of the interfacial engineering on the open circuit voltage and fill factor. For instance, this is the planar structure, normal planar structure. Usually the FTO conducting glass, you put the tin oxide or TiO2, whatever. Tin oxide is probably better than TiO2 because of the some UV stability. And then you probably deposit the perovskite on tin oxide, the ETL, and then the HTL material, and then the electrode on the top. In that case, if you introduce the some kind of functional materials in between the perovskite and the tin oxide, because the tin oxide perovskite interface is heterojunction, so you created probably imperfect the interfaces. And then if you introduce some kind of the bifunctional material with the chemical bonding with the perovskite and both the tin oxide, then we found that the open circuit voltage increases here, and then there is no significant change in short circuit photocurrent density, and then we slightly increase the fill factor. So this is a very good theoretical study, and then and also in addition to this increase in open circuit voltage and the fill factor, we also see the stability. So why the stability? This is actually the not the top top side. This is bottom side, but the intrusion of the moisture comes the contact not only the top here is here also we can consider some moisture the intrude. So therefore here if you introduce this if you have some phenol or the some imperfect the junction between the tin oxide and perovskite. So this the imperfect site is initiate instability. So then once you have this kind of interfacial engineering between the tin oxide perovskite, you also increase the stability. And for the grain boundary engineering, there are some the methodology. One is we first introduced the non-stoichiometry. It's actually the first the approach. So we actually access the precursor chemicals such as methylammonium iodide for the case of MAPBI3. We introduced the some excess methylammonium iodide and then spin coat. And to make the using the Lucius acid based adductant method, using this kind of intermediate, and then finally after annealing this adductor film, we can get MAPBI3. If you have the stoichiometric precursor the composition, then you have the MAPBI3. But if you have the excess MAI, then where the excess MAI goes, then probably the excess MAI. This is a solid actually. Will be sitting on the grain boundary. So this MAI acts as the grain boundary passivation. So by doing this kind of the non-stoichiometric the grain boundary engineering, we can see that the open circuit voltage fill factor increases without change in short circuit photocurrent density. So interfacial engineering actually did really the effect to increase the open circuit voltage fill factor because of reducing the interfacial the recombination. And also for grain boundary engineering, you can also add some kind of additive. This is one example. You can choose any kind of the additive. Here's we choose some by considering functionality of the additive, and we use the melamine material and the included in precursor solution, and then did some spin coating and the heating this the spin coated film. And then this additive has some the simultaneous effect of increasing grain size and also the passivation of the grain boundary. So then you can see some trap density. Usually the comes from the grain boundary decreases by increasing the concentration of this additive. This is one example also. And when you add some additive in the precursor solution to the grain boundary for grain boundary engineering, then the functional group is very important. So the grain boundaries, usually the surface of the perovskite has some defect. So what kind of defect? Anion defect, cation defect? We have some question about this kind of the defect. So then if you use some electron donating additive or the electron withdrawing additive, you can figure out which defect is dominant. So we found that electron donating functional group increases the performance, but electron withdrawing group is opposite direction, decrease rather than increase, decrease the photovoltaic performance. That means we have some anion defect, iodide defect. So providing electron donating the group, providing electrons. So then also this kind of the grain boundary engineering increase not only photovoltaic performance but also the stability. For instance, I mentioned about the some ETL perovskite engineering, interfacial engineering, and then this is normal structure, and then the grain boundary engineering, and the third case is the HTL perovskite, the interfacial engineering. So in that case, usually we use the post treatment because once you make the perovskite layer, then the post treatment is an effective way to passivate the grain boundary or the interface between the HTL. Here we have some different approaches using the ion exchange reaction to make some second phase, a different phase of the top of the perovskite layer, using some because we know that the surface of the perovskite has the iodide defect. Therefore, we would like to exchange some anion by using some PF6 anion, and then we introduce some second phase of the perovskite layer having the different anion. And by doing this one, and then we can see the increased open circuit voltage and fill factor, and then also the decreased trap density. So this is interfacial engineering approaches. I gave you some examples. There are so many reports regarding interfacial engineering. So in terms of stability, so actually stability also related to the hysteresis of the perovskite solar cell. If you see the very severe hysteresis of the solar cell that you made, that means that you have large defects in the perovskite material or the solar cell. So the defect engineering is also very important to reduce the hysteresis and then guarantee the long-term stability. For instance, to reduce the hysteresis, this is the reverse scan, the forward scan. If you have the two scanned IV curve is not well matched, then you say this is the hysteresis. So we actually the input. This is not the millimole. This is micromole. Very tiny amount of the alkali iodide, such as lithium, sodium, rubidium, and potassium and cesium. Then we found that the potassium iodide gives almost no IV hysteresis. However, lithium iodide, even the larger cesium iodide, gives still the very severe IV hysteresis. So from this result, we calculated using DFT calculation, and then probably defect is related to Frankel defect. Frankel defect means that the corner sharing iodide is moving toward some interstitial site of the A site cation. So if you block this the Frankel defect by inserting certain the proper cation in this interstitial site, then probably you can protect the Frankel defect. So we actually found that small or the even sodium cesium is does not working well. It's not working well, but the potassium is always work very well. So this is actually this Frankel defect site is related to octahedral geometry. Then the potassium is is suitable for the octahedral geometry. So the potassium is working well. So we actually published this work, the JAX in 2018, and then we would like to see further investigate what's going on about the ion migration if we add the potassium ion here. So this is we worked with the German group, Professor Van Hüttner equipped this in situ PL mapping the system. So if you see the control device without potassium doping as compared to potassium doping, here we change the some bias voltage here. This is a real bias voltage, very low bias voltage, and then this is a this is a lateral devices using the same electrode here, and then for the 0 volt, 0.2 volt, 0.5 volt here is the control device without potassium doping. So at this the positive electrode, you cannot see any PL imaging. That means there is some destruction of the perovskite phase due to the iodide accumulation. However, potassium doping system is relatively quite stable. That is that proves that the potassium ion protect the ion migration. So now I'd like to move on some upscaling the issue, because we have to think about some commercialization here. So there is some the large area trial here. This area the certified efficiency recently is 7 10.25%. So if you technologically, if you well design the module, then probably you can get more than this efficiency. And if you increase the for instance, further the area, the module efficiency is certified 11.7%. But this is not big deal actually. The module technology is a well-known, well-established technology. So you can just use the well-established the technology. Then we can have the very high efficiency. So for large area coating, we actually need some very specific coating solution, differently from spin coating, the technology used for spin coat technology. So we actually developed a very special coating solution without having the polar apoptotic solvents such as DMS or DMF. We have the acetonitrile, and then this is a room temperature coating. You can see immediately we can have the very good the perovskite the film. And then here is the in detail. For instance, methyl ammonium lead iodide powder. First, you have to prepare methyl ammonium lead iodide solid sample, and then in closed system, you produce the methylamine gas from the methylamine solution, and then methylamine gas can dissolve this the MAPBI3 powder, and eventually you have the liquid type. Okay, so this is very amazing the process. We do not use any liquid to make the solution. Just we use the gas phase. So gas liquid the phase transition is due to the some kind of here gas molecule is adsorbed in this perovskite powder on the surface, and then this the adsorbed methylamine gas has some very stronger interaction as compared to free the gas molecule. So probably looks like the liquid structure. So can dissolve some part of this the perovskite powder and making some still cluster form. So we confirmed from the Raman spectroscopy that we still have the cluster of this perovskite phase. And because this is very viscous the liquid, and therefore we diluted using some acetonitrile, and then the coated using that kind of the blade coat. And then also we found that this the method produced a highly oriented perovskite film, and also from the TM and then X-ray diffraction patterns. And then from this the experiment we can get over 17% as average power conversion efficiency. And also the other technology for large area coating, you can formulate precursor solution, and then the methyl ammonium lead iodide, the methyl ammonium iodide, lead iodide precursor, the mixture is dissolved in the DMF, which is not good for the large area coating because of the high boiling point. And therefore we use the 2-methoxyethanol, and then the 2-methoxyethanol is lower boiling point is easily escaped from the large area. But still there is some problem, so we used some lead acetate to control some interaction between the precursor and also the solvent. And then from by doing this kind of the formulation technology, we can get the proper efficiency. And also recently we developed the bifacial stamping method. This is a perovskite printing method. Never tried this kind of the bifacial stamping. So I like to describe more in detail about the bifacial stamping method. First, you prepare the methyl ammonium iodide, methyl ammonium lead iodide perovskite, but very mild condition, not 100 degrees C. This is 65 degrees C. And delta FAPBI3 annealed at 100 degrees C. So this pre-annealed film has still a DMSO polar apoptotic solvent, okay? And then you just put, without any pressure, just put. And then the heat is 100 degrees C and 9 minutes. Then there is some kind of the ion exchange reaction happens at interface and inside of the film. Therefore, after this bifacial stamping process, you can get MAPBI3 with a very some surface modified structure, and also the black alpha phase FAPBI3 at the lower temperature, milder condition. Probably this is due to the small amount of methyl ammonium go into the FAPBI3, so stabilized at low temperature. And this method actually gives a higher efficiency, not only higher efficiency, but also very large area the device, the perovskite field. So we don't know, actually we could not prove that the mechanism behind this bifacial stamping method. Probably there is some the facilitated ion transport mechanism may be involved. So we are now studying to prove this facilitated ion transport reaction. And finally, I'd like to mention about the material issue. Material is very important. For instance, conventionally we use the precursor material such as the FAI and PBI2. In that case, when you use these precursor chemicals, so when you compare the high-grade PBI2 and the low-grade PBI2, then you need high-grade PBI2 to make the high efficiency. We don't know still the exactly what's going on about the low-grade PBI2, but probably impurity can play important role in that kind of some creating the defect. But also this high-grade PBI2 is very expensive, so it's not suitable for the commercialization. Also, the precursor mixture has some kind of the aging effect, so you have to control well the precursor solution. So therefore, it is not suitable for anyway the large-scale upscaling the process. So we thought that probably the powders, if we make the perovskite powder, then probably we can get even we reduce the cost and then we probably increase the efficiency and the reproducibility of the performance. So we use the low-grade PBI2, and also recently we prepared the PBI2 from the lead nitrate, even the further decrease the cost. So this is very not energy required the process at the room temperature. All the reaction did at the room temperature in air atmosphere, actually, without using some nitrogen or the argon atmosphere. So for instance, the precursor material MAI or FAI first dissolved in acetonitrile at room temperature, and then the powder of the PBI2 low grade is added to this solution, and then by string for some time, and then there is some precipitation. For MAPBI3 is black powder. This is a perovskite phase. However, the FAPBI3 case, at room temperature, we can get the yellow FAPBI3, which is delta FAPBI3, not perovskite phase. So delta FAPBI3 is better than alpha FAPBI3 for storage issue, because this is quite stable at room temperature. So we use the delta FAPBI3, and then we compare this is a high-grade PBI2, and this is delta FAPBI3 powder, and we continuously reproducibly obtained over 21% efficiency. And this actually using the powder method FAPBI3, and then we obtain the stabilized power conversion efficiency from the National Renewable Energy Lab. Actually, this is the Newport, kind of the proxy for the National Renewable Energy Lab, and we have the 21.07% efficiency. So we can get the very high efficiency, but we did not control precisely the interface between the tin oxide, the perovskite, or perovskite, the upper spiral compound. So anyway, this is very good news. And we actually, the 130 cells, we prepared over 100 cells, and the average efficiency around the 21% we obtained. So finally, I like to so many things are there are so many things to do for next decade. Actually, we have to increase further the high efficiency, being close to the theoretical efficiency of the 30% by controlling the open circuit voltage and fill factor. And then in that case, the interfacial engineering becomes more and more important. And also the stability. So actually, we did some stability test by encapsulation. We just take the technology from the organic LED for some encapsulation, and we confirmed that there was no problem in some standard condition at 85 degrees C, 85% humidity. Still, the device is working after encapsulation. Still, we are using the tin oxide perovskite and spiral compound. And also, for upscaling, the issue we have to consider some very stable chemicals, even low-cost chemicals, stable low-cost chemicals, and also coating method. We showed actually the DIBA coating as an example, but slot-die is also available. And therefore, the synthesized the perovskite powder is a kind of will be standard coating materials for the upscaling the perovskite solar cell. And finally, I like to emphasize that different from the silicon, the solar cell, the perovskite solar cell is fully recyclable. Okay, so that is very good news, because if we do not have a recyclability, then there is some waste the issue, like the nuclear power technology. So always the waste issue is very important. But there is a report about the perovskite solar cell can be fully recyclable. So this is very good news. And also the perovskite material is a very flexible material. Therefore, it is so far the best material for the flexible solar cell. Still, we need some kind of in addition to the photovoltaic technology, this material can be applied to any other optoelectronic the technology, such as the X-ray imaging or the LED system. And also, we need some kind of the fundamental study to understand what's going on about this material. For instance, the local structural change on the light illumination or pressure or temperature. Still, we don't know actually, because what's going on about this material, because this material is quite different behavior, quite different behavior from the conventional oxide semiconductor. So very interesting material. So with that, I like to thank to my students, and also still working very hard, my team members. Also, we have this is very important, because this is a live streaming. So we are still opening for the postdoc and PhD students. So thank you very much.
Thank you very much for this very nice talk with so many important information. So now I think that we can have some questions for Professor Park. So please, well, yeah.
Yes. Very, very interesting. What about leads?
About the lead toxicity, I mean. Well, so I can say that lead content, we actually in nature energy, we calculated the lead content, and the lead content is very comparable to the lead that we can found from the natural soil. Lead content is that much high, and also as compared to silicon soldering, the lead is much less than the soldering soldered in the silicon solar cell. But still, I think the lead 2+ ion is a toxic element. So we have to develop, like the cadmium telluride, we have to develop the fully recyclable process. And then if we protect well, then so we can guarantee we have to try to not to release the lead anyway to the environment by the recyclability. So, and also I like to mention that the PbI2, for instance, the perovskite will decompose to the some lead iodide, methyl ammonium iodide, and lead iodide, and then methyl ammonium iodide is will be evaporated by the gas methylamine or something like that. But the PbI2 in pure water, the solubility product of PbI2 is 10 to the -8. Is hard to be dissolved in water. So this is also good news. But anyway, so from my personal point of view, we have to find out any kind of the lead 2+ not to be released to environment by developing the recyclable technology. Yeah. Yeah.
Yeah.
Thank you for the talk. My name is Daniel. I have a question about IV measurement. I understand that the discussion is not closed about how to measure perovskite solar cells. Do we have to precondition them? What about dynamic IV? Do you have an opinion?
Oh yeah, so that's a very good question. We have some debate about the measurement system. Here I show that here. This is recently the Newport developed and then now certified by the National Renewable Energy Lab, and this is called the quasi steady state IV sweeping. So meaning that here is there is some current voltage parameter were measured under 10 points IV sweeping configuration and find out the stabilization. And then measure again. So it's nothing to do with some preconditioning or something kind of some additional bias condition, something like that. So this is now it's stabilized, so-called stabilized the power conversion efficiency. So usually in the laboratory we cannot guarantee the efficiency. If you send some device into the National Renewable Energy Lab or the Fraunhofer Institute in Germany, then they can adapt this kind of the standard measurement now. Yeah, so the measurement is now is not that much big deal. Yeah.
You seem very confident for Frankel defect, but perhaps you know that recently, or not so recently, in 1917, Xenocrat and his team were making a very interesting experiment. They were injecting iodide gas, and they observed the contribution and the decrease and the increase, the decrease of the conductivity due to iron, and conductivity due to iron is due to iodide vacancies, as you know.
Yeah.
And they observed an increase versus pressure of iodide, increase of conductivity of electron conductivity.
I see.
Bon. And this is a very clear demonstration that the defects, the point defects, which are very well known,
yes.
are essentially due to Schottky defect and not to Frankel defect. And there is another contribution, a physical contribution to that, is the fact that for the energy of formation of Frankel defect needs much more energy than the formation energy for forming Schottky defect.
Yes.
So there are two
Yes, yes.
confident?
Yeah, actually, frankly speaking, the point defect is the possible defect actually, because we are starting with the resistive memory system. That is due to the defect of the iodide and iodide migration, defect migration. So point defect is lower energy than the probably Frankel defect. But according to the DFT calculation, the Frankel defect also is very low in terms of some directional something, and then Frankel defect, they mentioned that about, because we would like to explain why the potassium only working and then the other element is not working. So the by calculation, this is a calculation, so we are not,
No,
yeah.
no. There are a lot of DFT calculation.
Yeah.
But these DFT calculation give a very spreading value concerning the energy of formation between 0.2 and 0.6 electron volt. But between 0.2 and 0.6 electron volt, this is a ratio of 3. This is very important for activation energy for the formation of these defects, of these point defects.
I see. Okay, so I will study further to figure out this kind of defect. Okay, yeah. Thank you.
Thank you very much for the very insightful talk. I had a technical question on one of the results which you've shown about the, you showed films for photoluminescence under voltage with or without potassium. And you could see photoluminescence decaying where perovskites was degraded. Those was fantastic pictures. And I was wondering about the time scale which we've seen in the movies. Is it real-time movies?
Real-time movie, yes.
Okay, so it's a matter of seconds.
Yeah, real-time movies.
Thank you.
Thank you very much for your presentation. I like very much also that you give to photovoltaics also the openings of chemistry. What is very important is that in the past, photovoltaics was very much related to solid-state physics, to devices, to semiconductors, and to physical methods. So what I like very much is that this is a clear demonstration that chemistry, like in nature, can give really also some very important input on the PV field. But I have a question concerning the preparation methods. You mentioned about the grain boundaries. My feeling is that it seems that when we look at the growth method, it could be possible to make quasi-epitaxial film, maybe by using some surface, some structure directing. Have you tried to develop epitaxial films?
Actually, that is a very good question, and then we are trying actually, and then we found that the epitaxial, this is not real epitaxial, but a little bit related to epitaxial, the structure, and then we found that very interesting the physics from this the kind of columnar structure.
Mm-hmm.
So this is very good because this is actually related to the gallium arsenide related the LED.
Yeah.
This is an epitaxial kind of the growth.
Yeah.
So it's very similar to our the perovskite. Usually we have some kind of it's not the vertical growth. This is a horizontal growth.
Yes, this is what I mean.
Yeah, so
horizontal
this is
growth.
not good the way actually.
Yes.
So we are thinking of, we tried, we are preparing the manuscript anyway. And this is very good idea.
And one point is interesting because you mentioned that the recombination at interface is very important. And what's the main difference between the 3.5 technologies and all the polycrystalline technologies, thin film technologies? Is that in that case they really master very well the epitaxial relationship between the whole transporting layer, because they can manage with all the fantastic 3.5 methodologies. So this is something, and epitaxy is very important in that case.
Thank you very much. Yeah, thank you very much. Yeah, I think so.
Thank you for your presentation. 감사합니다. In the case of synthesis powder, do you consider the mass loss? Actually, I think when we synthesis the perovskite powder, all precursor of MAI IPVF not transform 100% of perovskite. So I understand your purpose of synthesis further is to reduce the cost, but I think in the case of synthesis, we should also consider the lossless.
So you mean the yield?
Yes.
Yield is 93%, so over 90%, so there is no problem. So my student calculated the yield. If they export it like the industry, probably will increase further. So there is no problem.
Thank you.
Thank you very much. A very nice presentation. It was a wealth of results and very impressive. I'd like also to come back. Some experiment was personally this experiment where you show that the PL decay or the PL intensity changed when you apply a small voltage across a channel of perovskite, so similar to my colleague. And what I could see, I could infer from your slides that such a small voltage as 0.5 volts that drop across a huge layer would still result in a considerable drop in PL intensity. So even for the iodine, for the potassium iodine, so isn't that bad news also for the stability? And I don't know how to relate that also to the efficiency where actually you show that it's stable. So, and you have much higher voltage bias across the cell. And there, in your IV curve. So how could you?
Yes. So what you pointed out is stability.
With the bias, you apply a bias, you change the chemical potential of the ions, and this results in considerable change in the PL intensity. So in the quasi-Fermi level splitting, in the lifetime, and so on. And when you look at the full device, so that's on the channel. But when you look at the full device, obviously you have a high efficiency, and so it can sustain much higher voltage across the device than what you know.
Yes. Actually, for the measurement, we make some not real device system, but in that case we did not measure very long term. So in this the device configuration for the in-situ PL measurement, we did not measure the long-term stability under certain device condition. But from the full cell condition, we compare the long-term stability under the standard condition with and without potassium, and then with the potassium ion. Actually, we published. I did not input this data here in slide. But we confirmed that the pretty much long-term stability of the potassium doped sample, the device.
Okay.
I want to ask. Thank you, sir, for the presentation. Being an amateur in this field, I wanted to know how much have you worked on the large-scale implementation of this perovskite solar cells. Most of the time, when I listen to lectures, I see this is all experimental and lab in phase. How much focused are we for large-scale implementation, or is there large-scale implementation have been done earlier and with no results? I wanted to know some parts about that. Can you give?
So you mean the research activity for the large area?
Yes, large.
So we actually focused on the large area coatings and the module fabrication. So 2 years back. So it's probably the people now. Some the device groups is working on the large area. But I think the large area actually is except for the some spatial coating technology, the module technology is just there is no big difference in conventional thin film technology. So and also the small area technology can be transferred to the large area. We found that as compared to gallium arsenide or the other thin film technology, conventional inorganic thin film technology, so the thickness is not that much strong dependence on the film thickness. If there is some kind of the fluctuation, it's okay, it's acceptable. So this is good news for transfer from the small area to large area. Still, the stability issue. Now we are working on the module, the structure, and then the stability issue. But I think going further, And the stability, a small area is okay. I think the 1 square centimeter is okay. And then yes, but some people, including our lab, we are working on the large area and the long-term stability. Okay. Thank you, sir.
Thank you very much. Other questions? Wait, oh, okay.
You mentioned that cesium, small addition of cesium helped the stabilization of formaldinium, formaldinium lead alpha phase. And at first sight, this is for me surprising because cesium has also room temperature, non-perovskite delta phase. So I was wondering, what do you think is the mechanism in this case, and maybe also in other cases like for rubidium? Is it related to some local constraint, for the fact that the lattice parameter is different, and then this helps stabilize?
That is we actually observe the lattice constraint. It's reduce the lattice constant. Therefore, the very small, tiny amount of the cesium ion is stabilized the A site KG, and therefore the Fa ion is because Fa ion is in terms of interaction. Actually, the methyl ammonium cation or the former ammonium cation is less interact with some iodide in rhenium oxide structure. But the Fa is less than because of the lower dipole moment, the constant. Therefore, the Fa is less stable than Ma cation. And if you have this small amount of cesium ion, then the lattice constant decreased. Therefore, we stabilized Fa ion A site. Yes.
Okay, thank you, Pere.
Thank you for the very nice presentation. I was surprised by your last take-home remark. Your last topic was crystalline silicon is not recyclable.
Yeah.
So we are producing every year 100 gigawatts of tons of waste, similar to nuclear power.
Yeah.
It's a provocation, or can you elaborate on that?
This is actually because the 2 or 3 weeks ago I visited. I gave a talk at the EMPA in Switzerland, Zurich. This is a photovoltaic. There is a photovoltaic research group, and then the group leader asked me after my presentation, and then what about the cyclability? And then the silicon does not have any the problem in the cyclability. So the waste problem. There is waste problem. So I mentioned here that because recently my colleague actually found the fully recyclable the method. And then, for instance, if we use the FTO conducting glass and then put the perovskite and then we collected the perovskite and then using some the magnet from solution, and then this is fully recyclable. So I think
silicon is not.
Silicon is not.
Why? Why is not recyclable? I mean, that's what you want. You say takeaway message. Silicon is not recyclable. That's and you compare it to nuclear, which is for me very much.
So I do not know well about the silicon because I'm not expert.
It's a takeaway message.
Yeah,
I mean, it's your last message.
Yeah. So
all the audience know that they should stop. That's
yeah. So no, it's because according to the EMPA's papers, the suggestion. So I just mentioned that the silicon, as compared to silicon, this material is better in recyclability. So that's why I would like to.
Maybe more interesting.
I'm not talking about stop working on the silicon. Yeah. This is very dangerous because we work together, and because the first stage for commercializing perovskite is tandem structure. It's good the way,
Yeah,
actually.
I understand. I know.
And then the next stage is a single junction of the perovskite. After seeing that the stability of perovskite placed on top of the silicon in a tandem structure, if you see that the stability of the perovskite, that's good. The news to transfer to the single junction perovskite.
Emmanuel is doing single crystal perovskites. So has someone tried to do a solar cell on that? Have you tried already? Or, I'm not sure. Single crystal. Yeah, because this would be first stage for epitaxial or for.
Yeah, it could be interesting.
Yeah, that is actually the single crystal is very good idea, but the single crystal thin film is very difficult.
But you can do it.
Yes, but
It's not perfect single crystal.
Yes, with
Yeah.
dissolvent cap crystallization,
Yeah.
it's possible to have large surfaces that can be millimetry or something. And yes, the problem is that you need something which is
So the challenge is there, but I think, yeah,
Okay.
it could be possible. Yeah. Yeah.
Do not say that the silicon, start silicon is
It's what you have written.
so many discussions.
Mais c'est qui savent pas, c'était que vous, mais c'est.
Okay. So, we start there, maybe? Okay.